Welcome to Lecture 6, Section 1.3 of the text Elementary Linear Algebra by Ron Larson, 7th edition, Cengage Learning. Applications of Systems of Linear Equations. This is Dr. Gilbert, Eyabi. What are the goals? Number 1. We should be able to set up and solve a system of equations to fit a polynomial function to a set of data. Number 2, set up and solve a system of equations to represent a network. Let's start with goal number 1, polynomial curve fitting. Let's say you have endpoints in the xy plane, x1, y1, x2, y2, right up to xn, yn, and those represent a collection of data, and you are asked to find a polynomial function of degree n-1. It has the form p of x equals a0 plus a1x plus a2x squared plus an-1 x raised to the power n-1, and it is expected that the graph of this polynomial function would pass through those endpoints. The procedure to solve this kind of problem is what we call polynomial curve fitting. Now, if all x coordinates of the points are distinct, then there is precisely one polynomial function of degree n-1 or less that fits the endpoints. And what we're going to do next is to show you how to generate that polynomial. So to solve for the n coefficients of the polynomial p of x, we substitute each of the endpoints into the polynomial function and obtain n linear equations in n variables. And mark you, the n variables are a0, a1, a2, right up to an-1. So right here is our system of linear equations. All we have to do now is to set up the augmented form, use our row reduced capabilities in Math Studio, and get the values for a0, a1, a2, right up to an-1. Plug that back into the polynomial p of x, and we have our polynomial with the coefficients determined, and we can actually sketch the graph. Example: find a polynomial that fits the points -2, 3, -1, 5, 0, 1, 1, 4, and 2, 10. Solution: since there are 5 points, we use a 4th degree polynomial function p of x equals a0 plus a1x plus a2x squared plus a3x cubed plus a4x to the power 4. What do we do next? Substitute each of those 5 points into the polynomial function, and we get a set of 5 linear equations with 5 unknowns. And the unknowns again are a0, a1, a2, a3, and a4. So quickly get the augmented matrix. Use your row reduced capabilities of Math Studio, and we have a0, a1, a2, a3, a4, and the required polynomial is given. And we can even go further back into Math Studio, plug in our polynomial exactly as it is, and hit plot. And this is the graph of the polynomial function right there that actually passes through all those 5 points. Remember to set your x min, x max, y min, y max to be very low so that you can get the actual shape of the graph. Quick question: can you locate all those 5 points on this graph? I leave that as a simple exercise for serious students. Network analysis. Goal number 2. The basic assumption of network flow is that the total flow into the network equals the total flow out of the network. That's number 1. And number 2, the total flow into a junction equals the total flow out of a junction. Whenever you see a negative flow in a network, that simply means it corresponds to flow in the direction opposite to that shown on the model. Kirchhoff's laws. We're going to use Kirchhoff's laws to solve a couple of problems under network analysis. The laws are very easy. An electrical network is another type of network where analysis is commonly applied. An analysis of such a system uses two properties of electrical networks known as Kirchhoff's laws. The first one says all the current flowing into a junction must flow out of it. And the second says that the sum of the products I times R, where R is for current and R for resistance, around a closed path is equal to the total voltage in the path. And just for the sake of notation, in an electrical network, current is measured in amperes or amps, resistance is measured in ohms, and the product of current and resistance is measured in volts. And you see some of these symbols. The first one, a battery. The larger bar denotes where the current flows out of the terminal, and the next symbol denotes resistance. An arrow in the branch indicates the direction of the current. Now, this is a simple example. Determine the currents I1, I2, I3, I4, I5, and I6 for the electrical network shown below. We can see that's a closed path, a closed path, a closed path. All we have to do is apply Kirchhoff's laws, and this falls down like a ripe banana. To make this easier for us, the solution to this example is actually what is known as lecture 7 in this class. In that lecture, I present the solution to this problem and the solutions to a couple of other similar problems under network analysis. Thank you very much.